Semiconductor fundamentals. Conductivity range. Semiconductors sit smack in the middle between conductors and insulators. Pure silicon at room temperature barely lets electrons move, but hit it with a little heat, light, or voltage, and suddenly it conducts. That on-off magic is exactly what lets your devices think in binary. Temperature dependence. As temperature climbs, more electrons gain enough energy to jump into the conduction band, boosting conductivity. But too much heat also unleashes unwanted leakage currents and speeds up device wear. Engineers design cooling strategies and choose materials to strike just the right thermal balance. Energy bands and bandgap. Valence and conduction bands. In a crystal's energy landscape, electrons occupy discrete bands. The valence band is full, the conduction band is empty. Only electrons that absorb energy equal to or greater than the bandgap can leap into the conduction band and carry current. Role of the bandgap. The bandgap size dictates how easily electrons cross over. Silicon's 1.1 eV gap blocks room temperature conduction, yet lets modest voltages trigger current, perfect for reliable switching. Wider gaps, like gallium nitride's 3.4 eV, suit high-power, high-frequency apps. Intrinsic versus extrinsic semiconductors. Intrinsic semiconductors. An intrinsic semiconductor is pure. Its electron hole pairs form only through thermal energy. In silicon at 300 K, that yields about 1 into 10 to the power of 10 carriers per centimeter cube, too few for most gadgets without further engineering. Extrinsic semiconductors. Doping adds deliberate impurities. Pentavalent atoms, e.g., phosphorus, donate extra electrons, n-type. Trivalent atoms, e.g., boron, create holes, p-type. By tweaking dopant type and concentration, we dial conductivity up or down by orders of magnitude. The P and N junction and diode behavior. Depletion region formation. When p-type and n-type regions meet, carriers diffuse across the interface, recombine, and leave charged ions behind. This depletion zone's built-in electric field blocks further diffusion, creating a voltage barrier. Diode 1 to 5 characteristics. Under forward bias, the barrier shrinks and current flows past 0.7 V, silicon. Reverse bias widens the barrier, letting only a tiny leakage current pass, until catastrophic breakdown in specialized diodes, like Zeners, used for voltage regulation. Conclusion. Semiconductors are the unsung heroes behind every digital advance, from your smartphone's processor to solar cells harvesting sunlight. By mastering fundamentals like bandgaps, doping, and junction behavior, you gain the toolbox to understand, and even design, the next generation of electronic marvels. If you're hungry for more, dive into device physics, explore cleanroom fabrication, or tinker with simulation software. Hit that subscribe button, share your questions in the comments, and let's keep pushing the boundaries of what semiconductors can do.